Welcome to the office. We want to continue taking a look at factor groups here. And what we've done so far is we've actually talked about factor groups where we have a normal subgroup to create the quotient and discuss the factor group or the quotient group or G mod H with respect to that normal subgroup. That's not how we were initially introduced to the idea. We were actually, well, I suppose our initial introduction was strictly through cosets back in section 10. But our most recent understanding was actually through the use of homomorphisms and getting a kernel from a homomorphism. To observe that we have a normal subgroup. So what I'd like to do is I'd like to consider the perspective of factor groups from homomorphisms, okay, grabbing onto that kernel. And again, because of our discussion that we just had on factor groups from normal subgroups, we really don't have anything to add, right? Nothing of substance. We have this kind of basic idea of having a homomorphism and then some of the characteristics that we can pull from that, right? Some more mapping ideas, which are very important to us, absolutely. But what we want to do is we want to recognize that that we can but there's not a lot to show, right? So this theorem says let phi a mapping from G to G prime be a group homomorphism with kernel H. And the cosets of H form a factor group G mod H, right? That's not surprising at all. We have, since it's a kernel, then it is a normal subgroup. Therefore, we have that it is a factor group where the multiplication of left cosets is defined in this way. Okay, so none of that is new. Okay, we have that. Also, the map mu from G mod H into phi of G defined by mu of AH defined by phi of H is an isomorphism. Now, this is actually a mapping that we had considered in a previous discussion on cosets. So this mapping, I didn't give it the name mu, but I essentially created this isomorphism from the cosets to images, right? And that's how we observed that the cosets and as we had this equivalence relation, and we observed that the equivalence classes of our equivalence relation were the same thing as our cosets. Same thing. So there was an isomorphism between them. And that's exactly this that they're talking about. The cosets and the equivalence classes of that relation where phi of A is equal to phi of B, then A and B are related, right? Then that's an isomorphism. It's exactly the same thing that we talked about in that previous section, previous discussion. So both coset multiplication and mu are well defined. Of course, we already specified that coset multiplication and proved that coset multiplication is well defined. We just maybe want to consider mu now. So what does it mean for mu to be well defined, independent of the choices A and B from the cosets, right? So what does it mean to be well defined? Well, it's well defined if we have the same inputs giving us the same outputs, but different representatives for those same inputs, right? So A and B, if AH and BH represent the same coset, then mu of AH should be the same as mu BH. So that's essentially what we're looking for. We want to make sure that if B belongs to AH, then, so we already know that BH is equal to AH, because this is just grabbing onto a representative of the set. So if we have that, what we want is for mu to be well defined. We need to have precisely that mu of AH, which we're saying is phi of A. We need to have that this is equal to phi of B, which is mu of BH. Again, we already know that. If it's the same coset, right? If this is in that we're saying that's the same equivalence class from that equivalence relation that we discussed in the previous section. And because of that, again, previous discussion, we get exactly what we're looking for. Since we can observe that A, H is all of the things G in G, such that phi of G is equal to phi of A. And that's our understanding of it from an equivalence class relation viewpoint. Indeed, mu is well defined. Okay, so we have that phi of A is phi of B. So mu of AH and mu of BH are going to be the same when A and B belong to the same coset, based on our previous understanding of the equivalence relation there. All right, so if we want to show that it is an isomorphism, then all we need to do is show one-to-one and onto. So let's let AH and BH belong to G mod H, and assume, let's see here, assume that mu sub AH is equal to mu, mu of AH is equal to mu of BH. There we go. That's what I wanted to say. Then, of course, that gives us that phi of A is equal to phi of B. But again, that equivalence relation of how we find our cosets, or how we can represent our cosets, this implies that B belongs to AH, and therefore BH is equal to AH. Thus, B is one-to-one. Excellent. So we have one-to-one. We have injective. And we have, let's see here. Let's see. Sorry, I got distracted by, we have a definition here, and I don't have it written down, what it looks like to verify. Oh yeah, no, I do have homomorphism property there. Excellent. So we have one-to-one, we want to show onto. So let's let Y belong to the of G. What am I showing here? I'm showing that mu is an isomorphism. Mu is a mapping from G mod H into phi of G. So now I'm grabbing onto something in phi of G. Two things from the domain, giving me the same output, mean that the inputs were the same. Onto, or one-to-one. Start with something in the codomain, and I can find something in the domain of G mod H. So since Y is an element of the image of phi, there exists an X belonging to G such that phi of X is equal to Y. And that would give us that mu of XH is equal to phi of X, which is exactly Y, which is what I was looking for. Excellent. Thus, mu is onto, or surjective. Therefore, mu is a bijection. So now that I have it's a bijection, I just need to verify that it satisfies the homomorphism property. And once I have that it's bijective and satisfies the homomorphism property, then yeah, it's an isomorphism. That's the definition. So it is a bijection. Now I just have to verify homomorphism property. So for AH and BH, elements of the quotient group G mod H, we observe that mu of AH times BH, this is equal to mu of A times BH. And by the definition of mu, this is phi of AB, but phi itself is a homomorphism, so this is equal to phi of A, phi of B, and this is precisely the definition of the image of mu of AH times mu of BH. It satisfies the homomorphism property. Thus, mu is an isomorphism. Fantastic. That's all that we really wanted to discuss here. Again, the theorem itself isn't much new. It just introduces to us this idea of mu, a mapping from G mod H into phi of G, which is an isomorphism, which seems a little bit weird, but again, phi of G, right, there might be a lot of things in G. There might be a lot of things in G that map to just a few things in the image in G prime. But what's going to happen is when you condense, you get just that sub collection. So 50 things might map to 10. Well, 10, that's it. And then when we take that mod, G mod H, that's 10 equivalence classes. And so we get that correspondence, 10 things mapping to 10 things. That's what we're looking at there. All right. Examples, lots of examples. Join me in the office for exactly that.